Well, if they're later in the morning, they're like, I'm hungry.
Yeah.
Let's see. Okay, that'll work. I believe. Okay. All right, guys. So one more time. Anything from that test? Yes.
So the current average is your grade, or is it just?
Yeah, your current average. So everything bold and underlined is about you. Everything in parentheses is a class average, right? So currently the class average in here, everybody's average averages out to be 73. You can see that in parentheses. Yeah, so for each thing, the quizzes, the tests, I tell you what your grade is, and I tell you what the average for everybody was, right? So this last test, I didn't curve it, and an average of 74, but you'll notice the distribution of the grades, nobody got a D, so 7 people passed, 5 people failed, right? But nobody got a D, which is interesting. But we have an ever decreasing sample size happening in our class, right? And by the way, just so you know, we have like 17 enrolled in here still. So today I didn't quite get 1/3 of the class to show up, which is exciting. Yes?
Well, what was it on the first day? What was the original,
It was like 20 something. So, I mean, I haven't lost a ton of people, but we started with 23 maybe at most. 20 something, 23. That was the original number of people. Yeah. So you're asking?
No, yeah, I was curious.
All right, so anything else from the grade sheets, from the test, anything? It all makes sense, what you did wrong at the moment, okay. So again, you can make corrections on that test. It's due by the day of the next test, right? And also, if you see anything incorrect on here, like there's a corrections to quiz that I didn't update or something, or I say I'm missing homework that I really shouldn't be missing, just tell me after class, right? So part of the reason, one reason I give you these grade sheet summaries is so you know where you are, but another reason is so you can double check what I've got in the computer, right? Because trust me, one time one of my professors put my 86, he put it in the computer as 68. It's just a human, we do that shit, so thankfully I noticed that, right? I'm like, wait a minute. Okay. Let me know if that makes sense, that sheet. Okay. So, what I find funny, and I didn't put this on here to like push any political agenda or anything, but the global temperature problem, right? So one time I had a student write on there, I know what you're trying to get me to say. I'm like, it's just the data. It's just the data. Right? There's controversy about what's causing that, but there is zero controversy about the fact that it's happening. Right? So, but there are people that say it's different factors. It's only like 97% of all scientists that say it's us. So, you know, so who knows? It's a coin flip. Okay. One thing that was on the practice test, if nobody has questions from the test, that I want to revisit, because I don't think I put it on here. No. By the way, before I get too far away, can anyone tell me when it is I'm supposed to use this adjustment here? So 2 things have to happen, right? We take a sample, and what else has to happen? So 2 things have to happen for me to know to do this, right? So if I do this, if I say the mean is 20, standard deviation is 3, and I have a normal curve, what's the probability that I get something less than 16? Okay, let me stop for a minute. You guys can copy that down if you want to, or you can just watch. If I put that information, you should immediately be able to draw this situation, right? Can you guys take a second and try to draw this situation. Three, six, seven, eight. 3, 6, 7, 8. Hey, we did it. Hey, Ron.
Hey.
All right. What's the graph look like? Of course. The graph in the sucker. Normal, which means bell shape. I love it. If I would have said uniform, you would have made a big rectangle. Right? So in that one problem on the test, where I told you I had a uniform distribution, some people were drawing the bell shape. But I want you to see, it's nothing tricky, nothing. If it's uniform, it's a big ass rectangle. If it's normal, it's a bell shape. What goes right in the middle?
20.
Yeah, what always goes in the middle is the mean. I love it. So are these z-scores yet? No. If they were z-scores, what would go in the middle? 0, because by the way, real quick. Was there a question I told you was going to be on the test? Remember that question I told you was going to be on the test? Yeah, so I had very few people get it right, even though I told you. Okay, so what does a z-score tell you about a data point? How many standard deviations away from the mean? So if you just say the distance from the mean, I'm going to be an asshole and say in miles, right? So you have to say the number of standard deviations away from the mean, right? And again, I really, so if I'm, where am I at? I'm here, right? There's the mean, there's the 16. So I am below the mean. So can you tell me anything about this area here, which is less than 16? Can you tell me anything about that area? Is it big? If I do all the work and I get the answer to be 90%, does that make sense? You guys see that? Your picture is supposed to help you. So the mean cuts it in what? Half. So below 20 is half of the picture, yes? So below 16 should be less than half. So if I do the work to this problem and my answer is 90%, it doesn't make any physical sense. There's not 90% of the picture right there. So the picture is supposed to help you tell if your answer makes physical sense. So I know already it's going to be less than 50%. Do you guys see that? Okay, maybe. So can anybody tell me what's the next step to figuring out this area, this probability? Where would the answer sit? Where does the answer to this problem sit? I mean, you have something that you can just go look the answer up, right? What is that thing? Z-score chart. Okay.
You have a spare z-score chart?
Yes. You're gonna need that today.
Thank you.
Cool. You're welcome. Okay. All right. So this problem right here, you should be at the point where you're like, oh, thank God it's just this. Right? In order to use the z-score chart, which has all the areas for a normal curve, that's what it does. The z-score chart has all the areas for a normal curve, and that's exactly the problem I've got. I obviously have to make 16 become what? So I can use that chart.
Decimal in it or
A z-score, right? So I have to convert 16 into a z-score. And of course, how do I do that? What's the formula for z-score? Yeah, it'll be the number I'm interested in minus the mean. Why does that make sense? Because a z-score is basically how far from the mean to a data point. But then I divide by the standard deviation to see how many of these fit in there. How many 3s are between 16 and 20? That's the question. So that really is how many standard deviations are from the mean to the data point. Okay. So what is that? What do you guys get if you do this? Negative 4/3, which is about what? I love it. And of course, why do I round it to 2 places? Because the chart only goes to 2 places, right? Now, Nico, can you help me? Can you look up negative 1.33?
Yeah.
I'm sorry, bud.
Oh, no, no, you're good, you're good. Is 0.0918.
0.0918. Okay. So that is the area in this, which means it's the probability that I get less than 16. So if I have a group of people, let's say the average age is 20, standard deviation of the ages is 3. And it's normally distributed. And I'm like, if I pick one person, what's the probability I get somebody who's 16? That's not terribly far away from 20, but it is more than one step. Do you guys see that? If I go one step down from 20, what age do I end up at? If I go one step down from 20, I end up at 17. So 16, this z-score makes sense then. It's a little more than one step down. Negative 1.33, it's a little more than one step down. Because one step down would be 17. And the further I go down, what should happen to this area? What if I would have said 12? Would the answer have been bigger or smaller than this? If I said the area below 12, would it have been bigger or smaller than this? Smaller, because it's got a smaller freaking tail. There's less stuff in there. You're further away from the mean, so it should be less likely to get way the shit out there. That's why the z-score chart makes sense. As I go further down, my area gets smaller and smaller, right? So if you start, like if you look at the negative z-score side, and you start going up, the areas get smaller and smaller because I'm going further and further away from the mean. That's why this chart makes sense. There should be a connection between where the hell I am, z-score, and what area there is. That's why the z-score chart existing makes sense. Yeah, maybe. Now, so that problem's done, right? There's like just a little over a 9% chance that we would pick somebody who's under 16 years old. Okay, so what if I ask this instead? Same setup, I'll say 1A. B, same stuff, except now I take a sample of, what you got, Jeff? 11 people. And I ask, what's the probability that X bar is less than 16? This is fundamentally the same question as this, except instead of picking one person, I'm picking 11. And I really want the idea to make, the more the ideas make sense, the more you know exactly what to do. It's not a memorization of situation. No. This standard deviation tells me for individuals. That's why it makes sense in this problem, because I'm picking one person. So can I use that same number for this problem? I'm not taking one person. So what do I have to do? Yeah, I've got to do this thing. The very first thing I've got to do, I can't use 3 because that's for individuals. I need what's true for a group of 11. So doing this makes the spread become what's true for a group of whatever size. Bless you, will like you. So what the hell is that? It's like 0.94. I don't know. Does that sound good? What is it?
9045.
9045?
And begin with 4 decimal.
9045?
45.
45? So would it be 5?
No, the end of 2.
So it's 904, go further. Go further.
5, 3, 4.
Okay, so then you can round it to 905. I love it. Now, you could use 9045. I don't care. It's got to be at least 3 places. So if you want to go more, feel free, right? But it's got to be at least 3 places. So that, I didn't circle that, sorry, to be the answer. I just circled that to be what this is. So we've done one thing so far in this part B. We just changed the standard deviation. Now here's the thing I really want you guys to get. I just do all the same shit we just did. Except, instead of right here, instead of a 3 there, I'm gonna use 0.905. So it's still the same picture. In reality, it's gonna be a little skinnier, but you don't have to draw it. 20 is still here, 16. But now when I go to make a z-score, I have to use the new standard deviation, 0.905. That's gonna be like negative 4.2, maybe?
Yeah, rounded.
4.2?
Negative 4.42 rounded.
4.2, okay. Let me stop for a minute. So right now, this should be like oh, thank God he gave me that problem. This right here needs to be, oh, cool, it's just this kind of problem. Just make a z-score, look it up, right? Then this, I took a sample, I asked a question about the sample mean, which means I do this and then I do all the same work, right? So if I look up negative 442, what's true about that? If you try to look that up on the chart, what's gonna happen?
How are we able to look it up? It's only it only goes
Beautiful, right? What's it say? What's the lowest number you can get? Negative what?
Negative 3.5 and lower.
There we go. So if you use the chart, there would officially be 0.0001.
Okay.
In reality, it's even less than that. Because that 3.5 steps down is this, and I am even further down. Are you guys with me? Didn't I go further than 3.5 steps down? I went almost 4.5 steps down. So that's why I would accept either this or this. I really want that to make sense because the chart sort of stops at 3.5. If I keep going from 3.5, won't there still be less and less and less stuff out here? If at 3.5 is this, if I go further, so at 3.5 is that, if I go further and further and further, it's going to be less and less and less. So that's why I say if it's off the chart, it's either 0% of roughly or about 100%. So this should make sense. If the average age is 20, and I take a group of 11, what would you put money on their average age being? So the average age of everybody in this area is 20, and I take a group of 11. If you had to bet, what would you bet that the average of those 11 are? The average of everybody's 20. I take a random group of 11. I would put money on their average being 20. So is it likely their average is actually less than 16 when the real average is frickin' 20? No, it isn't. In fact, look, it's crazy unlikely. So a lot of what we're doing is formalizing stuff you knew already. You intuitively know this. If the average 20, and I take 11 people, I expect their average to be close to 20. It's not going to be far from 20. This is freaking far from 20. That's why the probability is really low. Okay, maybe. Okay. So again, this is an example like that global warming problem on the test. So the part where I said we took a sample of 5 or 7 years, that's where you have to do this. Okay. Okay. All right. So let's do a problem that I put on the practice test, and I did it for a very specific reason. I didn't put it on the actual test just because. Let's see if you guys remember how to do this. So if I have a normal, in fact, let's say standard normal distribution. Can you guys take a minute and figure out what the two z-scores are that patch the middle, let's say 95%. What are these two z-scores here? We've done that problem before. What sucks about the area I give you versus the area that the chart understands? What area does the chart understand?
Everything below.
Everything below a z-score, right? So do I know currently right now, looking at the picture, the area below any of the z-scores I want? No. Don't I want this z-score right here? Yes. Can I figure out the area below that guy? Yeah. What would it be? 2.5. If there's 95% in there, there's 5% out there. I don't know why I'm suddenly from New York or something. There's 95% in there. Out there's 5, so this will be 2.5%. Does that make sense right there? You can always do this. If I want the middle whatever percent, you just figure out what's outside of there and cut it in half. You could do that for any number I put in there. Now take a minute and see if you can look up this. Is this a z-score? Right here, is that a z-score?
Yes.
Nope.
Uh,
It's an area,
X.
right?
X?
It's an area. Do you see that? Where are areas on the chart?
No, there's
On the outside is the what? What are these on the chart? Or like this for you guys. What's on the outside on the chart? You could do it. What's on the outside on the chart? What's on the
the
outside?
numbers.
For what specific? What kind of numbers?
Like, to solve either the lowest or the highest. Or
They're the z-scores,
the C-scores, yes.
right? The z-scores outside. What's in the middle?
Oh, I didn't look at
Wax on, wax off. What's in the middle? The areas, right?
Yes.
So, it kind of makes sense if I know a z-score, I can look up in the chart to see the area. I should be able to do that backwards. If a z-score relates to an area, then an area should work backwards to be a z-score. So you're gonna look up 0.025 in the body. So try to find 0.025 in the body of the z-score chart. Let me know if you don't have a chart.
And that's the negative side right there, where 0.025. That's 0.025 is on the negative, right? The negative side.
Yeah, it's on the negative side, exactly. So
Okay.
you know you're gonna look at the negative z-score side.
All right.
If you look at the positive side, the lowest you can get is 0.5000, which is way bigger than this, so you gotta, yeah. So you're looking for 0.025 in the body. 0.025, what do you guys see? Yeah, you can get this exactly. This is one thing that actually works exactly.
I got 0.4013.
So again,
Yeah.
this is not a z-score.
Oh yeah. Oh.
So on your chart, you got z-scores out here. You want to look in the body to find 0.025.
Oh.
So let's see.
Oh. It's
You
in negative 1.96.
So let's see real quick. Let me show the rest of you guys. Okay, Panasonic. We understand. You're amazing. Okay, there we go. Yeah, 0.025, 0138, 017, I'm getting closer, 0212, I'm getting closer, 025. Will you always be able to find exactly, oh hell no, this is just, we got lucky, right? We try to find the closest one. So, real quick, you guys do me a favor. I'll come back to that in a second. If this z was negative 1.23, can you guys, don't say anything, look up what that area is, please. Don't say anything. Just, I want to know what that area is if that's negative 1.23. Don't say anything. Okay. Let's see, somebody that I haven't heard from yet. Can you tell me what area you get for negative 123? Now's your time. This is a nice, easy question. Anybody tell me, what do you get when you look up negative 123?
Is it, point 1093.
1093, let's see, negative 1.23, 1093, right? Okay, and we've been doing that shit for a while now, right? Isn't this roughly 11%? You with me? So, if I told you instead, if I didn't tell you this and I said, I want the z-score that has 11% in the tail, wouldn't you find 11% the closest you can get? And then you would see, oh, it's negative 1.23. If I know a z-score, I can look up the area. If I know the area, I can look up the z-score, right? This goes both ways. Can you convert from dollars to euros? Yes. Can you convert from euros to dollars? Yes. Math goes both ways. Be jealous, right? So if I look up, coming back to our problem, 0.025, I find 0.025 right there. Beautiful. What z-score is that? Negative 1.96. Do you guys see that? So normally I look at a z-score and then I see what the area is. If I give you an area, you find the area and then you look out to see what the z-score is. So this chart just converts between the two. Z-score to area, area to z-score. So this z-score would be negative 1.96. So what would this be? Yeah, because of symmetry. If that's negative 196, that's positive 196. Okay. So, if in a hat, I had all the z-scores on the chart and you picked one out, what's the probability that you would pick one that's in here? That's between negative 196 and positive 196. What's the probability? Not a trick question. How much data do I catch between these two? 95%. So what's the probability that I pick a data point that's between these two? 95%. Maybe. So if I start at the mean and I go up and down about 1.96, and by the way, do you guys remember within 1 there's 68% in a normal curve, right? What about within 2 standard deviations? There was 95%, right? So do you see how negative 196 and 196 are rounded to 2? So within 2 standard deviations, there's 95% of the data. Okay, it's all kind of like coming back, right? It all comes back, okay. All right, let's do this. I want you guys to do everything we just did, but I want it, yeah, that's good, Jeff. I want it instead for find the 2 z-scores that have 90%. Do exactly what we just did, just find the 2 z-scores that have 90% between them in the middle. By the way, just so you know, we're doing a lot of this kind of problem because it's exactly what the idea is behind the next chapter. Which I think is chapter 8, is that right? Yeah, chapter 8. It should be interesting position on the Z-score chart. Oh, I'm sorry. Is that a Z-score? It's a percentage. So if you draw the picture, it's the top 4%. So it's really kind of related to what we're doing. If you draw the picture, top 4%. So what's below that? So you have to look up 0.96. Because it's an area, it's a percentage, it's not a Z-score. So you know the area, you gotta find a Z-score. Gotcha. The formula used is correct, but you put, so it's mu plus Z sigma. And Z should be these, not something from the negative.
Because I tried solving for it.
Oh, that's what that is.
Oh, I do this right.
Oh, that's what you, okay.
Versus one, but now I am 96 instead of 34%.
Yeah, 0.96, and then see what the Z-score is. Yeah. All right, guys, what's the first step on this one? Anybody? First step on this one. So you want this Z-score and you want this Z-score.
0.05.
Yeah, so 90% in the middle, there's 10% outside, 5% on that side. Why do I have to do that? Why can't I just look at 0.9? Because is 90% the area below any Z-score I want? No, if I look up 0.9, I'm gonna get the Z-score that has 0.9 all the way below it. That's not what I want, it's not what I want. So I've gotta look up 0.05, because there's 5% in both of those. What happens if I try to look up 0.05? Something interesting should happen.
They give you a little star.
Yeah, it's one of these little asterisks, because do you see how 0.05 is right in the middle of these two? This one's 1.64 and this one's 1.65. So they just split the difference and make it 1.645. Now real quick, why does that make sense? If I go out 1.645 steps, I catch 90%, correct? If I go a little further out, should I catch more or less stuff? So if I go out 1.645, I catch 90%. If I go a little further out, am I going to catch more or less stuff? I'm going to catch more stuff. I'm casting a wider net. So it makes sense that this is 1.645 to catch 90, and it's a little bit further out to catch a little more. So if I wanted to go to 99, would the Z-score be bigger or smaller to catch 99%? I'd have to catch more. I'd have to go further out to catch more. Right? So if I start in the middle and I only go this far, I'm not going to catch very much stuff, am I? It's going to be a very small percentage. I got to go further and further out to catch more and more. Okay, maybe. Okay, so this is all kind of laying the groundwork for the next chapter, chapter 8. Okay, so now let's kind of transition into chapter 8, and then I'll bring this back really soon. So, oh yeah, I meant to do this. Shoot. If I take a sample, let's say that we're curious about the percentage of people that are going to vote for Donald Trump, right? Let me just utter the name. By the way, please keep it to yourself, whoever you're going to vote for. Let me see if I can remember my freaking password. So if we wanted to know the percentage of Americans that are going to vote for Donald Trump, can we talk to every American? Do you want to talk to every American? No. About how many Americans are there? And how many people in the country that are able to vote are there, roughly? Do you guys know? Huh?
3 billion.
Holy shit. All right. No. Yeah, roughly 300 million, right? There's 340 million people, so like 270 or 280 million people that could vote. Are you guys with me? I don't want to call 280 million people, do you? Even if we split them all up amongst us. Screw that. So of course, what do we do then in statistics? When I have this huge ass group I want to say something about, what do we do? Okay, take a sample. Really, right? So if I want to get a feel for what percentage of people are going to vote for somebody, I would take a sample and contact them, right? Now, of course, it's got to be a random sample, so I'm going to have to pick people from every state. If I only pick people from Wyoming, is that going to be representative of all the United States? Oh, hell no. So that was the purpose of chapter 1. And he said we can take a sample. You want to make it truly random, which means you just have to pick. Everybody in the population has to have a chance, right? So listen, guys. So we pick a sample of, give me a number. What sample do you think we should, how big of a sample do you think we should take? 40. Okay. Does 40 sound like a decent sample to represent America? 40 people. To be really honest, 40 works, but what's the trouble with 40?
Everyone in every state is counted.
Exactly. One thing is, like, there's no way to make sure that we get somebody from every state. So, what's the smallest sample size we should take? What do you think?
50.
Okay, good. All right, based on what I just said, it should be 50, but the absolute smallest would be 31. Does anyone know why? What's magic about 30? Yes, if I take samples greater than 30 size, it'll become normal when I plot the means, right? Okay. 50 sounds good because then you get at least one person from every state, but is one person from every state, does that really represent? Okay. So statistically, 40, 50 work. Do you think the uncertainty, do you think we're going to be more uncertain about what we find if instead I pick 1,200 people? If I only pick 40 people, how certain are we going to be about our results versus 1,200 people? Do you guys understand? The bigger the sample you take, should you be more certain or less certain about what you find?
More.
You should be more certain about what you find, right? So there's kind of a sweet spot kind of thing going on. You don't want it to be too little, or else you're really uncertain, right? You would tell somebody, I think it's going to be between 20% and 60%. Is that useful? If I said, I think 20 to 60% is going to vote for Trump, is that useful? No, he could totally lose or he could totally win. That's not useful. So maybe that's what I get from like a sample of 40. Maybe my uncertainty is really big. So the larger the sample we take, the more certain we should be. So if I take a sample of 1,200, then maybe I'll say it's somewhere between 42 and 48%, right? Now that makes more sense. That actually is useful information. Let me stop for a minute. Does that by itself, that should make sense from day one. We want to take a bigger sample because then we're more certain about what we find, right? Okay. So mathematically, the sample size should show up in the equation that we're going to use, right? So we're going to develop an equation that actually gives us that spread. So very often what you'll see in the news is Trump. Let's say the Republican primary, Trump, DeSantis, and then whoever the hell else. There's other people that are putting their hat in the ring, right? Are you guys paying any attention to, or do you guys understandably like, I don't want to hear about any of this shit? Anybody paying any attention to the politics of stuff? Anybody? A little bit?
He has 34 felonies. Trump.
That's a good thing to know. That's one thing. Now again, in general, right? Charges against somebody aren't evidence that they did something wrong. But probably okay. So we want to get to a point where we can say, like this is 46%, and this is looking to be like 25%. But at the bottom of the screen, if you ever see a poll like this, somewhere it should say At the bottom, it would say plus or minus 4%. What does that mean? How many from the analysis that was done here, what percentage would vote for Trump between what and what? Plus or minus 4%. So what percentage did we get from our sample? 46%. Plus or minus 4%. So between what and what? Yeah. Add 4 is 50. Subtract 4 is 42. 42% to 50%, right?
Why 4%? It's just like a random number?
So this comes from the analysis. In fact, we're going to learn the formula for this. This isn't just something they make up like, are you sure? I don't know, plus or minus 4%. No, it's based on a number of factors, one of which being the sample size. So if they took a bigger sample, this would go down to 3 or 2. Again, the bigger the sample you take, the more certain you should be about what you see. Does that make sense from day one? Of course you want a bigger sample, right? Okay. So that number, we're going to learn the formula for this number, right? Whether you want to or not, we're going to learn. Okay. And I don't know if any of you have ever seen anything like this anywhere you've ever looked at. Somewhere it says plus or minus 3, plus or minus 4%. Okay. So what about DeSantis? What's his range? Let me write this better. So this is 42 to 50, right? Because it's 46 plus 4, 46 minus 4. So what's DeSantis' range? 21 to 29. From this analysis, could we comfortably say that Trump is going to win the Republican primary? Or that there is, let me say it this way, there's good evidence that Trump will win the primary? Shit, yes. Right? All right, let me make sure you guys understand why I can say that. What if somebody else took a poll and they got Trump 40% and DeSantis 32%. And down at the bottom it said plus or minus 5. So what do you guys think? Who does it seem took a larger sample? What do you think? Which one of these two does it look like took a larger sample? These guys, because they're more certain. There's less uncertainty. They more than likely took a larger sample.
So less is more and more is less?
Yeah, this represents uncertainty. So how do you make the uncertainty go up? You take a smaller sample size, right? How do you make the uncertainty go down? You take a bigger sample size. So and from this analysis, it looks like Trump is from what to what? Yeah, 35 to 45. And what about DeSantis? 32 minus 5, 27. 32 plus 5, 37. Can we say from this analysis, can we say that there's good evidence Trump will win? What's the difference? Why can't we say this one shows evidence that Trump will win?
Because 37% is close to Trump's close one.
What do these two intervals do? Do they overlap?
Yes.
Yes. So Trump goes from 35 to 45. DeSantis goes from 27 to 37. There is overlap. From this analysis, could the percentage of people that vote for one or the other be the same? Or could there even be more that votes for DeSantis than Trump? Yes, do you see that? So this one, good Lord, Jeff, this one I can say, there's good evidence that Trump will win the primary because these do not overlap. These show there's a difference. This one, they overlap. So can I say that Trump will definitely, there's good evidence that he will win. I can't say it from this analysis. Let me stop for a minute. Now, of course, we're going to get into the math of this. How do I calculate all this stuff, right? I just want you to understand the idea before we get into it. Maybe. Okay. So, by the way, well, let's see. We're not gonna start with percentages. That's a little bit freaky. So let's start with means. So for example, if, and by the way, well, let's see, how do I say this? All right, let's talk about means. So, you know, for example, if I took a sample and I got a sample mean of 25. All right, so maybe this is, I don't want to do ages again. Let's say this is the number of mistakes somebody makes on a quiz. So the sample mean was 25 mistakes on this test, right? There's 25 mistakes is the average number of mistakes. And then say the standard deviation is 10 or whatever. Okay, this is getting a little too specific, Jeff. So I want to be able to calculate an interval around this that catches a certain percentage of all the means. So let me ask you this. So let's say in this one, let's say we took a sample of 40 people. From everybody who took this quiz. So there's like thousands of people took this quiz. You with me? And we take a sample of 40. Is the sample mean, do you think it's going to be the same as the actual mean of everybody? So let's say there's thousands of people took this quiz. We took a sample of 40. Would the sample mean be the same as the actual population mean? I would put money that it won't be, and I make teacher salary, so that's big. I'm going to put money on that, right? So more than likely, the real mean is not 25. With me? So we don't know if it's going to be above or below or whatever, but our best guess for the real mean right now is 25. That's our best guess. So here's the idea. I want to go up and down a certain distance from 25 so that I catch, let's say, 95% of all the data. Okay. So the real mean is sort of out there, right? So the real mean, let me draw a picture again. Let's say the real mean is there. And we find a sample mean of 25. So I want to go up and down so much to catch 95% of the data. Let me ask you this. So, let me see. There's a decent analogy that I try to use. Does anybody fish? Okay, neither do I. Okay, I don't even like fish, to be honest. But this analogy is good. Let's say you're go to a lake, and there's a certain fish you want to catch, right? There's this certain fish. It's the legendary big-ass freaking bass. Big-ass bass is his name, right? Just this huge bass just been in the throat. If I throw out a tiny net, and somebody next to me throws out this big-ass net, which one of us is more likely to catch that specific fish? Obviously the guy with the big-ass net, right? When I have a sample, we take a sample, we don't have a clue what the freak the real population mean is, right? So if I took a sample of people and got their average age, that's not the real population average age, right? So that's like the fish. We're trying to catch that freaking real mean. So what we're going to do is we're going to take our sample mean, and I want to go up and down. If I go up and down so that I catch 95% of all the data, what's the probability that I actually caught the real mean in there? What's the probability I caught any specific thing? So if I catch 95% of the fish in the lake, what's the probability that I caught that one fish I wanted to catch? 95% chance. The guy next to me catches 80% of the fish in the lake the next day or whatever, then it's only an 80% chance that he catches the one fish he wants, right? So we take our sample mean, and I want to go up and down so that I catch 95% of all the data, then there's a 95% chance that we actually got the real mean. Okay, maybe. Okay. So let's do this. Let me get a more concrete example. Let's see. Yeah, okay. Yeah, we could use that one maybe, okay. All right, let's try this. So, we've already done part of this work. Can anybody tell me what up here tells me that the sample means will be normally distributed? What part of what I told you tells you that the sample means will be normally distributed? There's a magic
30.
number, yeah. Why is it normal? Because n is bigger than 30, right? So the sample means will be normally distributed. Okay, that's huge. So for these problems, they either have to tell me it's normal or the sample size has to be more than 30. Right? In this problem, I did not say it was normal anywhere. So thankfully, my sample size saves my ass. Okay. Now, I want to know, let me see. I want to know how far out I've got to go to catch 95% of the data. We already know that. We looked that up earlier. Bless you. How many steps do I have to take up and down to catch 95% of the data? We got it more specific. So 2 from before was our estimate. Earlier today, we figured out exactly what it was.
Oh,
Do you have that written down?
negative
1645 was for 90%.
negative 1.96.
1.96. So if I go down 1.96 standard deviations and up 1.96 standard deviations, now let me be careful here. Yeah, let me do this. Okay. Then I'm going to catch 95% of the data. Okay. So this is all built on stuff you came in knowing. You knew when you came in first day, you knew that if I took a sample, it wasn't going to be the real population. It's just close, right? So what this is doing is it's trying to improve the estimate. If I just told somebody the average is 25, that doesn't really tell me. If I tell them the average is somewhere between 10 and 40, well, that tells me something. That tells me they're kind of uncertain about what the mean is. Okay, now, next thing is, did we take a sample?
25.
Yes, we took a sample of 40. Not the sample mean. Are we talking about sample means? Yes. So what's got to change? Standard deviation's got to change. Let's see, 10, what will it be? 10 divided by
25. Or
Nope.
square root.
square root of? Nope. 25 is the sample mean. I need
Oh, number.
Yep.
40.
40. All right. Somebody help me out. I think it's going to be 1.5 something. I could be really wrong. Let's see.
1.58.
Oh, not too bad. 1.58. Keep going.
1, 3,
1.58.
1, 1.
1, 1. Okay, good. So we got to go at least 3 places for standard deviation, right? Okay. By the way, guys, I don't know if you noticed. Right now, we're in what I call the conceptual stage of shit, right? So we're talking about the concept. I'm talking about freaking throwing nets out and catching fish. right? So this problem right here is gonna be a little bit all over the place because I'm talking about the idea. We're gonna then do a problem clean and just show you all the real steps you're gonna take, all the nuts and bolts steps you're gonna take to do these kind of problems, right? So if I start at the mean and I go up and down 1.96 of these, right? So before we do that, I want to show you kind of what's really happening. So we're gonna finish this problem up right here in a minute, but I want to take a sidestep and really show you where this formula comes from. Do you guys all remember this formula here? Right, does that look familiar? So that's just the z-score formula solved for x, right? So this is what I would need if I wanted to find a raw score that has an area somewhere. I would have to eventually use this formula here. Now, let me write this part of it down. In general, we do not know what the hell the population mean is. If we're doing a study, we're going to take a sample. We are not going to have a clue what the hell that is. So instead, we're going to use our best guess. Okay. And then we're going to go, well, let's see. Leave this blank for a second. Z is still going to be here, but can we use this? Well, we took a sample to find the sample mean, so this has to become the new standard deviation, right? Just like we did right there. Okay. And this is if I want to go one specific direction, but we know we're going to go up and down, so it's going to have a plus or minus. That is the formula for these things. And what these things are called, they're called confidence intervals. So that is the formula for the confidence interval. It is exactly what we're about to do here. I would take the mean plus or minus 1.96 of those. Now, it's been a long time since this has happened, but at some point I had somebody ask me where the plus or minus key was on the calculator. Right, but obviously I got to do it. So normally what I do is I figure this piece out first, and then I add and subtract it to 25. So can somebody help me out? What is 1.96 times 1.581? I would say 3.04. I don't know, just making that shit up. Whoa, 1.96 times 1.581. That's all I want.
Oh.
Yeah, just that piece by itself. Whoa, okay. Let's say 3.099. Sure. All right, so to get the actual to get the actual interval, there it is, you would do 25 minus this and 25 plus this. All right, so it'll be 21.901 to 28.099, I believe, if I did that right. I think so. So you can even write it like an interval, 21.901 up to 28.099. So from our analysis, is there evidence that the actual average is 30? What do we think the actual average is contained in? Between what and what? 21.901 to 28.099. So is there evidence that the actual average is 30? No, 30 is not in there. Is there evidence the actual average could be 27? Hell yeah, because it's in there, right? So if somebody said, you know, I think the average number of steaks is 30, and then we take a sample, and we do all this work, and then we get here, we're like, I have the evidence you're wrong. That's what this is. This is what you do to clinically test something. Have you guys heard that phrase? Clinically tested to blah, blah, blah. We're trying to find evidence of what it can do. So if it's a medication, I try to see what's the average number of minutes until the headache goes away after you take this medication. Is it less than the other drug? This is the kind of analysis we would do. We would give it to people, and then we would compare the average time to relief versus the old drug average time to relief. Right? So if this was the number of minutes until your headache goes away, and the old drug took 30 minutes, is this clinically shown that our new drug is better? Do you guys see what I'm saying? This shows that it doesn't include 30. It's actually less than 30. This is evidence that the actual average time to relief is less than 30 minutes. So this, in my commercial, I could say, it's been clinically shown that our new drug will relieve your headache faster than the old drug, right? Okay. And you're all like, please give that to me. I need statistics. I need pain relief. Okay. Okay. So let's do a clean problem, because this was all over the place. I really want you guys to see what just a straight up nuts and bolts problem looks like, because this was all over the damn place. Okay, here we go. All right, let me put the formula back up at the top here. So example, we take, we take a sample of, I should have done one more thing, let's do it. We take a sample of 87 dogs and find an average tail length of 38.1 centimeters. That's got to, let's make it 40, no, 30 points. Everybody with me so far? So this is how we're spending our days. We're measuring dog tails. Do you think that this is the average tail length for all dogs? What do you think? Do you think the average tail length for all dogs is 38.1 centimeters? No. Because this 38.1 centimeters is just the average length of 87 dogs. There's a few more dogs than 87. So this is just a sample. But do you think that it's going to be close to this? Well, yeah, if my sample is random enough, the actual average should be close to this. Okay. We know, we know the population standard deviation of dog tail lengths is 7.11 centimeters. Okay. Find the 90% confidence interval for the population mean dog tail length. Oh my God. Okay. So what we want to do, we've got a sample we took. We want to create an interval out of it so I can say the actual, this interval is such and so confident to capture the real population mean. How confident are we going to be that our interval catches the real mean? How confident will we be? You can give me a number. what's the likelihood that our interval catches the real mean? You could do it. No, this is not subjective. I told you the answer to this question, it's up there. How confident, what's the probability that our interval actually catches the real mean?
38. Oh, and 90.
90%. If I construct a 90% confidence interval, how many data points did we catch? 90%. How certain are we caught a specific one? 90%. So can somebody help me out? All right. So I know I want to create a confidence interval. Confidence interval formulas will have the plus or minus in them. There's going to be 3 confidence interval formulas that we're going to end up with at the end of chapter 8. They're all going to have a plus or minus in them. Makes sense. I want them to go from something to something. Can anybody tell me what's X bar?
87.
Sorry?
87.
No?
38.
Yeah, X bar is the sample mean, and the sample mean was 38.1. Now what's N? 87. So N is always the number of things in our sample. What's sigma?
7.
Yeah, sigma is the population standard deviation, so that's 7.11. And now we just got to figure out what the z-score is, and we already did. Remember, earlier we did the 90%, did we?
1.645.
Yeah, 1.645. Now real quick, you don't have to put, remember when we did this, we found negative 1.645 and positive 1.645, remember that? Right, when we did that, we found negative 1.645, positive 1.645. We don't have to put that there because it's in the formula, right? That's why it's a plus or minus, so it can go down so much and up so much. And let me point this out right now. There's something on here I call the baby chart. So if you look way down here, so go to the positive side and look down in this corner. You see how it says confidence level? When they say critical value, they mean the z-score. So do you see how if I wanted 90%, it's 1.645? Do you guys see that? 95 is the 196 we found earlier. 99 is the 2575. Did we need this little baby chart to find those? No, we found them earlier. You know I'm going to ask you to make a 94% confidence interval. You know I am. So then you have to do it in the chart. You can't just use the baby chart. But I will say 90%. So you can just go right there and get the z-score, right? Okay. So do we have everything we need to construct that confidence interval? Yeah, we got X bar, we got Z, we got sigma, we got N. So now I can do 38.1 X bar plus or minus 1.645 times the old standard deviation divided by the square root of 87. Now, it shouldn't be too surprising. This part we call the error because that's the give or take, right? And you guys have heard this. If I'm like, how many people come in? 60, give or take 10, right? Isn't that something good to hear? Isn't that the uncertainty in how many people are going to come? That's how far off we think we are. So that's the error. Bless you. So I highly recommend you guys calculate the error by itself first, and then you can do the plus or minus bit. Right? So let's see what the hell that comes out to be. 1.14 maybe? No.
0.253.
1 point. Do it again.
253.
1.253. Okay. And now you just subtract that from 38.1 and you add it to 38.1. It's almost too nice to believe. So what's 38.1 minus this? 36 point
847.
847?
Yeah.
So like 85, and then if you add it, you get 39.35 roughly. So here's the part you're all gonna love. Okay, let me make sure you guys can read this sort of. Okay, here's the part we haven't done yet. The math is done, and then I need an interpretation of what the hell that means, right? Getting the number is great. Yay, number. But statistics is about understanding what the hell you just did. So here's what I'm gonna need for every confidence interval problem, right? As if you didn't already dislike me enough. Here's the thing, you gotta write a little something. So here's what I need to see. How confident are we about this interval catching the real mean?
Oh, wait.
We're not 100% confident, no. How confident are we that this interval catches the real mean dogtailing? And that's never something you have to work out. It's something they have to tell you. No. So confidence level is measured in percentage because what's the probability that this interval catches the real mean? We know what it is. 90%. If I made the interval bigger, would I be more or less confident that it catches the real mean? If I made the interval bigger, would I be more or less confident that it catches the real mean? So if I'm in a lake and I throw a little net out, how confident am I that I caught a specific fish? Not very. If I throw a bigger net out, will I be more confident that I'm going to catch a specific fish? Yes, because I'm catching more fish, so there's a higher chance I'm going to catch a specific fish. So we are 90% confident that the interval 36.85 centimeters to 39.35 centimeters contains the true, well, I won't say true, contains the population mean dogtail length. So nuts and bolts wise, when they give you a problem and they say, find the whatever percent confidence interval, you know you got to figure out what you got to see. Did they tell me this? Did they tell me sigma? Did they tell me n? And can I figure out what z is? Z is always going to come from how confident you want to be, because you can control how far out you go. If I go further out, I catch more stuff, I'm more confident. So real quick, that problem is done, right? That problem is done. We did the work, we got the interval, and we said our little statement. What if I had all the same stuff, but instead of 90%, I wanted to be 99% confident? What would have changed? All the same information, except I want 99%. What would have changed? Z-score. What would the Z-score have become?
2.575.
Yeah, 2.575. So let's see real quick. 38.1, give or take, 2.575 times 7.11 divided by square root of AC. So when I see this equation, did you hear how I read this? My sample mean, give or take, this many of these. So I'm going down and up so far. And how far am I going to catch 99%? So see what we get. Somebody help me out with the error piece. Let's see, what's it gonna be? It's like almost, I'd say 1.88. Making this shit up as I go. But I think it's 1.88. I don't know. Maybe like 1.9, somewhere around there. And 1.962. So then you would go 38.1 minus 1.962. Oh, what the hell is that going to be? It's going to be like 36 point something. 36.138 maybe? If you do the minus. What is it?
40.06.
Oh, the other one is 40
Oh,
point.
sorry.
062?
Yeah.
Is this one right? I did that in my head. Who knows? I don't know if I can trust myself.
137.
137? Oh, because you rounded this different? Okay.
Yeah, you're right on that.
Close. Okay. Let me ask you a question. Can you guys see? Just look at this interval and this interval. Can anyone tell me which one is wider?
I believe that one.
Why?
It's higher. The numbers are higher.
Yeah, well, this goes further that way, right? And this goes further down that way.
Yes. And this one goes further down because since that one's less than 40, it goes further down this way too.
Well, no. So this only goes down to 36.85. That goes down to 36.13. It goes a little further down.
Okay.
So this interval goes from this to this. That interval goes from a little less to a little more.
Oh, okay.
Why does that make sense? If I want to be more confident that I actually caught something, do I have to go further out or not as far out? I gotta catch more shit to be more confident that I caught something. So if I want to be 99% confident, my interval's gonna be bigger because then I'm catching more stuff. If I only want to be 90% confident, I don't have to go out as far. So how would you get to be 100% confident? Is there a way to get to be 100% confident? Well, mathematically, you would just have to go down to negative infinity and up to infinity. Then you would be 100% confident. And so, I don't know if I've said this yet. I don't think I did, but one reason I love statistics, right? And you're all like, great for you. But one reason I love it is because it's the most honest math. Statistics says, I don't know. Statistics says, I can tell you how likely this is. This is freaking life. Are you ever certain about much of anything in life? Are we? Are we ever certain about something in life? No. So statistics is the most honest math. It's like, I think it's 38.1, give or take something, it's the best I could do for you, right? If you try to use math to predict what lottery numbers to pick, you're going to be very disappointed. The best you could do is to get possible probabilities of what's going to be good to pick. That's the best you could do. Now, does that mean statistics isn't worth shit? Well, no. Remember what about my little brother? Did I tell you about my little brother where he's like, Jeff, what? It's going to be a 50% chance something happens or not. It's always 50-50. I'm like, oh, don't become a doctor. I would rather hear my doctor say there's a 96% chance you'll come out of the surgery okay, instead of a 50-50. No, screw you, doc. You got to know better than that, right? So there's this fine line between people believing statistics can do too much for them and people believing statistics does nothing, right? It can't tell me for sure what the hell's going to happen, but that doesn't mean it doesn't tell me anything. It tells me what's the most likely thing to do. Do any of you guys play poker or watch poker?
I've seen this movie that's based on poker with Matt Damon.
Rounders.
Yeah, Rounders.
Yeah.
It's the only experience I have.
You guys all aware of poker? You know what poker is, right?
Yeah.
Okay. So the really good poker players know probabilities and statistics. That doesn't mean they're gonna win every time, but they're gonna play in a way that increases the probability that they win overall. So they know they're gonna lose sometimes, they just know they are. But in the long run, if they play a certain way, they should come out ahead. That's the best thing we can do, right? And without a knowledge of statistics and a knowledge of pot odds is what it's called, blah, 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 how much money's been put in, blah, 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 you can't do that kind of thing. You just have to hope you get lucky, and that's not a great hope, right? Okay. Yes?
All the homework, are we gonna see like binomial or like the other distribution?
Confidence intervals are based on normal
Okay,
distributions.
okay.
Yeah, so like chapter 6 and chapter 7 are really, really getting us all the basic tools we need for chapter 8 and chapter 9, right? So this is chapter 8, it's gonna be confidence intervals.
And then one more thing about the homework, because I know the homework is very picky. Are we gonna see like more pickiness, I guess, like in the homework of this question? Like, is there gonna be like more?
Well, let's do this. Let's take a problem out of the homework. Let's see what the hell the homework's gonna look like. That's a good question. Because homework sometimes,
I'd rather have an example of what it's
yeah,
supposed to be.
I'm with you. So let's see, here we go. Alright, let's see, bum, 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 bum. Okay, good lord, okay. This is kind of a problem, it takes forever to get to the point, but okay, we'll try this one. I'm gonna freeze this, because let's see. Freeze. Okay, so let's take a look. So read through that. It starts off mean age for all Foothill College students. Oh shit, did I cut it off? Let me try to get it better. Unfreeze. Okay. Let's see what I can do here. I'm gonna freeze my hand on there. Give it. This is the best part of class. Okay, here. I think you guys have young eyes, you can see that. Freeze! Okay. So the mean age for recent fall term was 33.2, population standard deviation has been consistent at 15, blah, 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 right? So this is what a confidence interval formula, problem is gonna do. It's just gonna give you all this information. So what's your first thing is to identify all the information they gave you, right? So for example, that 33.2, what symbol do I give to that? What is that N? Is that sigma? Is that, what is that?
It's the sample.
Is it what now?
Oh, wait, no, that's the number. Okay.
33.2. What is that? Is that N?
That's
Is that Z? Is that sigma? Can't be N, because you don't want to take 33.2 people. You got to chop one of them up. I really don't want you guys to chop anybody up.
So then it's just the sample.
It isn't the sample, it's the sample what?
Me.
Mean, yes. The mean age was 33.2. Right? So that's what it was. So that's actually, this problem, I love it. The mean age back in the day was 33.2. That's what it was. Population standard deviation, 15. Now we take a sample. So what's 25? Suppose that 25 winter students were randomly selected. So what's 25? What variable? "25 students are randomly selected." What letter?
Oh.
N. The mean age for the sample was 30.4. So what's the sample mean symbol? X bar. I love it. So this number they gave us was the population mean a while back. So the question is going to probably, well, I don't know if they actually asked us this. Blah, blah, blah. Oh, screw all that crap. We're gonna change the problem here. We are interested in the true mean age for winter foothill college students, okay. So we got X bar, we got N, we got sigma. All we're missing to be able to use this formula is the z-score. So eventually they tell us to blah, 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 construct a 95% confidence interval, right? So can somebody tell me, if I want a 95% confidence interval, what's the z gonna be? 1.96. So I wanna go up and down this many steps. So now I can use the formula. X bar, give or take this many steps. And then I just have to fill it in. So go ahead and try to work that problem all the way out to the interval. Oh yeah, I should have went to the homework, yeah, that's better. Shoot, that's okay. So now I get, if I put X bar here, 30.4, give or take, 1.96 of these, 15 over the square root of 25. Now one big thing, one big problem I have, and this book does this every now and again, is that sample size big enough?
No.
No. Somewhere they say you have to assume it's normal. If I assume it's normal to begin with, I don't need the sample size to be 30 or bigger than 30. This book is a little bit loose with that. So then I calculate the error. You guys calculate the error here. 5.88.
88, Yeah.
Okay. And now you just have to do this minus this and this plus this. So again, if I just say the average looks to be 30.4, that's not really true, because that's just my sample mean. But if I say the average looks to be somewhere within this interval, that's being more honest. That's kind of communicating to somebody how certain I am about the sample I took. So this would go from 20, what? 4 point,
52
thank you.
to 36.28.
Yeah. What was this? Mean age, yeah. So then the statement at the end would be, we are how confident?
95.
Yeah, we're 95% confident that the interval (24.52 years to 36.28 years) contains the true mean age. I say true instead of population all the time, so I'm just going to continue. The true mean age of a winter foothill college student. Winter foothill student. Okay. Okay. So the nuts and bolts, what you see all the time in statistics is the nuts and bolts of work, doing the work is much simpler than the concept behind it would make it seem. But I do want to end today up talking about the concept more generally. Okay. So everybody got this here. Last thing for today. So, in real life, we have a situation where we don't know what the real mean is. Right? Do you know what the real average foot size is of people in Wyoming? I don't have a frick. Are you kidding me? What would we have to do to actually determine that exactly? Wouldn't we have to go measure everybody in Wyoming, their feet? Now, there's a lot to that makes me not want to do that. Right? There's a lot of people in Wyoming, not like compared to other states, but still, there's a lot of people in Wyoming, and I really don't want to mess with their feet. So, what do? We go take a sample. Now, the sample mean we get, I'll bet a ton of money that it won't be this. Are you guys with me? If I just take a sample, almost definitely the sample mean won't be the same as the real mean. Are you guys with me on that? So it just would fall somewhere. So let's say we happen to get a bunch of Bigfoot people, right? So randomly we could just happen to get a lot of people whose feet are a little bit bigger. And that's why the sample mean would be up there. Then we construct a confidence interval. And let's say we make a 95% confidence interval. What the shit does that really mean, Jeff? Good Lord, what the hell does it mean? It means this. We did this. Are you with me? We went, took a sample, we got a sample mean, we constructed a confidence interval. Ours happened to catch the real mean. Are you with me? A different group of people. Couldn't they go to Wyoming and take a completely different sample? Their sample mean might show up here. And so when they make a confidence interval, 95% again, did their interval catch the real mean? No. So what does it mean then when it's at 95% confidence interval? That means if a lot of people went and made their own confidence intervals from their own samples, 95% of them would actually catch the real mean. 5% wouldn't. So that's why there's a 95% chance that our interval actually catches the real mean. There's a 95% chance of that. Why? Because 95% of all confidence intervals would catch the real mean. Only 5% wouldn't. Maybe. That's why we state this the way that we do. When we make an interval, there's so much of a chance that the interval we make catches or contains the real mean. So there's a 5% chance that our interval doesn't have the real mean in it. That's pretty good for me. I don't know about for you. 5% chance I make a mistake. Hey, that's pretty damn good. I like that. 95% chance I'm right. That sounds pretty damn good. So with any report you see that says 68% of people like to have e-cigarettes or whatever, right? That's a sample. Somewhere they have to tell you plus or minus what percent. Somewhere they have to tell you how off they think they could be. Okay, maybe. So I think that's enough for today. So next time I will bring my a worksheet for you guys to work on, and I'll show you a few real life studies and show you where they constructed confidence intervals. Yes, 8.1 is exactly what we just did today. Yeah, and to be honest, I think I put this on the homework sheet. We're going to do 8.3, and then we're going to do 8.2. Let me tell you why. 8.3 still uses z-scores. 8.2, well, you're going to love this. We're going to have a different chart. It's going to use a different thing, and I'm going to explain why it uses a different thing, and somehow it relates to Guinness beer, about why we use a different thing than the z-score. Okay, so a little teaser. All right, guys.